Welcome to Power System Protection course. We are discussing on distance link. In this lecture, we will talk on power swing detection techniques. Continue with that, we will be addressing the other techniques on power swing detection methods. 3 techniques: continuous incremental current calculation, the R-Rdot approach and the rate of change of swing center voltage techniques for this perspective. So, in the last lecture we discussed about 3 techniques based on the rate of change of impedance, so concentric characteristics, blinders and continuous impedance calculation. We discussed about both power system blocking and out of step tripping, and we demonstrated examples on stable swing, unstable swing and fault, how the relay is able to distinguish them. We will continue with that with more methods available in this domain which are being used in different relays. So, first one is your continuous incremental current calculation, only current based. Second one is R-Rdot, that is a derivative of resistance and the rate of change of swing center voltage. The swing center voltage we will define that, and then we have its rate of change. So, let us start the first one, continuous calculation of incremental current. So, we know that both voltage and current varies, they vary, I can say that significantly during swing situation. All the 3 phases, observe this, the continuous calculation of the incremental current, so the delta I incremental current, or literature says about superimposed current also. The method computes the difference between the present current sample value and the value stored in the buffer 2 cycles earlier. So, 2 cycles earlier value and the present value, they are being compared, and we calculate the delta I for each sample. Like here, you see here, you can say that the delta I, you can say that this is the this point and this point 2 cycles. So, that is why this and this compare delta I. So, this point and this point. So, then this becomes your delta I and like this. So, this is the swing situation, swing trajectory, and we find this delta I to be significant. Normally, the delta I will be steady state. So, magnitude will be same. So, it will be 0. But during fall also the delta I is expected to be high, but once the fall persists, you can see that then the delta I will be negligible. We will see that perspective. What the method does, that the method declares a power swing when the absolute value of the measured incremental current, its absolute value of delta I is greater than 5% of the nominal current of the system, that the same condition is present for duration of 3 cycles. So, if the consecutive 3 cycles 50 hour system 60 millisecond around, if this situation persists, that the delta I magnitude becomes more than 5% of the nominal value of current, then this is the relay declares this as a swing situation, otherwise not. The advantage of this continuous calculation is that it detects very fast power swings, and also the corresponding particularly for heavy load even including heavy load condition also, because it is superimposed component based. Now, let us see this situation as an example. So, this is a swing situation, swing trajectory for the current. So, we go on, you can say that delta I compute, you can say that from the 2 cycles. So, this one 2 cycles before this. So, this to this. So, this you can say delta I value. So, you go on calculating the delta value. So, see this magnitude of delta I. So, that can be being done here, you can say that for 3 cycles you can do like this. Now, this is a fault situation and suddenly the current jumps. So, at this point you can say that compared to 2 cycles this becomes significant, but if you see this point here inside the fault, because due to decaying DC it will die down, and then you can say that the goes to the steady region, then this point and earlier 2 2 cycles, you see here consider the delta I becomes negligible as compared to the swing situation side. So, this clearly shows that if you find the corresponding delta I for a period of time like we mentioned about 3 cycles, then the swing can be clearly identified from fault situations. So, this is what being used in this approach of many relays use. You can say this principle to distinguish, to identify power swing. The R-Rdot approach is used for out of step tripping specific utility only. So, we know that the when the apparent impedance becomes smaller than a value, then the relay distance relay should go for a trip decision. So, with that philosophy that if the z is smaller than x z value, then the relay will trip. With that concept, you can say that this principle is being taken from. So, this is to identify unstable power swing. So, for that what is being done, a dz by dt also is taken into consideration, including that z minus some z setting also. Note z minus z setting becomes negative when the apparent impedance is inside the characteristics. That results in a trip decision. Now, what is being done, z minus z setting plus some k into dz by dt kind of thing, rate of change of impedance to accommodate in the swing perspective is being added. In furthering that theory, what is being done, that instead of impedance, the real part of that gives you the resistance, and that you can say that the approach you can say uses in that perspective. So, what is being done in the a line, you can say that straight line is defined in the R-Dot, R-Dot means dr by dt and the r x axis dr by dt, y axis. A line straight line is defined based on the same principle what I mentioned on the impedance. R minus R 1 like Z minus Z 1, this is Z setting, R minus R 1 plus T 1 some constant into dr by dt. So, if this is you can say that less than 0 means negative, then the corresponding you can say that thing is called an unstable swing situation. So, this is the straight line which we are trying to define, and its slope is you can say that based on this is T 1, T 1 you can say that dr by dt. So, then you can say that we say you can say that here, so this you can say that the x axis intersection point is R 1. So, what happens here, that this y the output of you can say that this control output for this equation. So, continuously you can find out the dr by dt from the real part of this impedance, and then R 1 is a setting value, T 1 is a setting value. So, then we can compute this y. When the y becomes negative, the corresponding can say that system, the y becomes negative in this zone, then the system is declared as unstable. Stable swing traverses path in this region, and unstable you can say that goes through this. So, it will go to the negative you can say this. So, thereby I can say that the corresponding relay can decide very quickly on the perspective of on the unstable swing, that is out of step tricking perspective. System separation is initiated when the output y becomes negative and the switching line is crossed by the impedance from right to left, subject that it traverses part like this, because this is the load area. So, in the load area you can say it traverses like this unstable swing, and it will not you can say cross the you can say line in case of stable swing. So, this is the simple approach being used for the out of step tripping perspective. Now, I will go to the last method, swing center voltage approach. So, on this you can say that we will define what is swing center voltage, and then we will proceed further. Let us consider a system like this, and we have a source impedance local one Z s and the Z r in the remote, and the line impedance is Z L. So, earlier we have defined what is electrical center. So, same can say that concept we are again continuing here. So, when the machine angle of the two side sources are 180 degree apart at a point in the systems, the voltage becomes 0, and that is called the swing center. That point where the corresponding angle becomes 180 degree and the voltage vanishes, that becomes swing center. We talk about electrical center, you can say that in the earlier discussion. The corresponding voltage of that center at different situations is the swing center voltage. Once again, we point out that what is the swing center point in the impedance plane, where you can say that the corresponding voltage becomes 0 during the 180 degree delta, and now you say you can say that the corresponding voltage at different situation of the delta, the corresponding voltage is called the swing center voltage. Let us define the EST, this side source is expressed in terms of the sinusoidal thing, and the ERT, this side source voltage becomes these sinusoidal things. We consider the power is flowing from left to right with an advancement angle of delta by this source as compared to the right hand side source. Let us assume that the corresponding swing center is m distance from this ZL per unit distance from this m bus, and this falls on the line impedance ZL. Now, we will apply the superimposed principle. So, each source applying one by one after the other. So, when this first source ES being there, so we say that the voltage at the swing center m distance from this RM relay. So, the voltage at the swing center contributed by this only this source, not this source is short circuited at that time. So, that becomes equals to the corresponding impedance from here to here is the Z1R 1 minus m Z1L Z1R which is sequence impedance 1 minus m Z1L this side upon Z1S Z1L plus Z1R, the total impedance of the system into this voltage. So, we are applying this voltage and we are trying to consider what is the corresponding voltage of this point. So, that from this side, because this is shorted. So, this side this voltage will be this one. When the remote sets acts alone and this side is shorted, the voltage at the swing center again from this side will be this side shorted. So, that will be Z1S plus m Z1L upon the total impedance of the line system into the voltage, this voltage is this voltage. So, we got these two expressions. Now, what we see that we know earlier also that this location is half up from both the sides. The swing center or electric center is half of the total impedance of the line ZS plus ZL plus ZR. So, that gives us, you can say that these two impedances which we are looking from this side or that side, what we have calculated in the earlier slide with Z1S plus m Z1L upon total impedance, Z1L plus 1 minus m Z1L upon total impedance, that becomes equals to half, because it points to that point only. So, if we assume ES ER equals to E, same voltage simplicity, then the swing center voltage at any instant or time t, that becomes equals to root t sin omega t plus delta t by 2 cos delta t by 2. So, we got this that both these sources are there, that is superimposing these two, whatever voltage you can say that is obtained at the m point, and with this you can say that relation of half with algebraic manipulations, we will get that you can say that this side source and that side source combine them, add them, you can say that we will get the voltage to be root 2 E sin omega t plus delta t by upon 2 cos delta t by 2. So, this term if we see here, it is multiply, we consider this magnitude of, we consider the corresponding swing center voltage, and this you can say that is about the sine of this angle, the delta t also. So, the corresponding swing center voltage is a function of delta t. Swing center voltage is independent of the system's source and line impedances, no impedances, nothing. It is only considered to the root T E and the delta perspective, and omega is considered the sleep frequency, a system frequency sin omega t 50 hertz system or so. So, therefore, they particularly attractive for using no setting power swing perspective, and this that is considered the beauty of this approach. Furthermore, the swing center voltage is bounded to be considered because the sinusoidal and this cos term we consider this is 0 and upper limit to 1 per unit. If you make it a per unit, you can say that if we have a 0 to 1. So, that is why I can say that another you can say that from the calculation perspective simplify the thing. Now, I will move forward. In our earlier discussion also, we have this kind of diagram on the impedance. Now, to this impedance if you multiply the I, then you get the voltage. So, then this becomes you can say that also the voltages. So, this is source voltage E s, this is V m, and this is Z s I, this is Z L I, and this is you can say that Z R I, that's it. And this straight line as we have discussed earlier is nothing but the total impedance of the line. So, Z into I you can say the dotted line. Now, if this you can say that is operating point at any instant of time. So, this you can say that voltage is E s, this voltage is relay voltage, this side is E R side voltage, and this you can say that the other bus voltage perspective. Now, let us consider the midpoint you can say that is O dash. So, this you can say that this swing center. So, the corresponding swing center voltage is S C B is this one O to O dash. Now, if you see this you can say that O S C B. Now, we have a similarity that this you can say delta when it traverses it makes 180 degree here, if the trajectory becomes on this path when k equals to 1, we have discussed earlier. Now, if you see this you can say there is similarity here, this V m is the relay bus which is measurable, this phi the corresponding current with respect to this V m at the relay bus during an instant of time, where it is the angle between these two sources are delta is delta. So, now you can say that V m cos phi on this perspective V m cos phi. So, that becomes equals to a very close to S C B with little difference. So, an approximation of S C B obtained from the locally available quantities, locally we are trying to make approximations that this V m cos phi becomes this. Note that the theta, this I z and theta, because line impedance is pretty more than 85 degree with an angle or so, then the theta will be close to 90 degree, and that leads to a situation that you can say in that perspective that the V m cos phi at this point will be considered very close to the swing center voltage. Any discrepancy also does not matter much because of the further discussions we like to have. The relation between S C B and the phase angle delta can be simplified to the following. So, what we see here, if you see this further this diagram, phi the angle between V m and the corresponding I at that point, but delta is the angle between E s and E r. Now, this phi is also angle you can say that this almost delta by 2. So, if you take this you can say that the corresponding E to be equals to E s E r perspective, then the corresponding V cos phi, so it is E cos delta by 2. If you take this one, then this is also an approximation to the swing center voltage. We are distinguish swing center voltage here to swing center voltage 1 because of this approximation. Agree? So, the swing center voltage can be approximated you can say that from this measurement, what is measurable V m and the corresponding phi, and from that you can calculate the swing center voltage, but this can be related to this swing center voltage where it is related to this angle delta. What you do now that with that swing center voltage S C B 1, if you take the derivative of that one cos delta by 2, and that gives us you can say that minus E upon 2 sin delta by 2 d delta by dt. So, this shows that the derivative of the swing center voltage is having only in terms of the delta terms and the voltage. The equation provides the relation between the rate of change of swing center voltage and the slip frequency d delta by dt for the two machine equivalent system. What is the advantage? It is the independent of source and line impedances, which are difficult to get, unlike in the earlier lectures on concentric circle or the blinder approach, where you require those ZT impedance and total impedance of the system or so. So, this shows that you can say that the derivative of this can be easily obtained from this one, and that you can say that will be indicative of, you can say that the situation of distinguishing swing versus fault and the unstable swing and swing perspective. So, what logic is being followed? The technique generates the blocking signal, parsing blocking signal, when it measures a significant value of swing center voltage derivative dSCV 1 upon dt, d delta by dt. I am saying that from that one, if you calculate the corresponding dSCV by dt, then you will find that you can say that it will be a very significant one. Parsing, for techniques to produce an output, the absolute value of the rate of change of SCV 1, we have to ensure that SCV value is of good value is there to check, you can say that its assurance that you can say that this is swing is passing through, and must be minimum threshold of minimum, you can say that value of rate of change of voltage, and the magnitude of SCV must be within a limit, maximum and minimum. Furthermore, the sequence impedance measured by the distance relay must be within a stator, you can say that zone, like the we talk about concentric circles and so. So, these are being satisfied, means you can say that the corresponding parsing blocking function can be invoked. It will ensure that this is going to be a swing business and the relay has to be blocked. So, we saw from the earlier discussion that the derivative of that one is having a d delta by dt, that is the swing frequency perspective. Now, let us consider take the same system and examples what we have discussed in our earlier lecture also, stable swing, unstable swing and fault, which are to be distinguished by this approach. So, what we do that for the stable swing, we created a fault and then we cleared this line, and then this relay considered observed swing. Second case, unstable swing, we delayed the clearance of this fault. So, then you can say that this observes the unstable situation, and then we create, you can say that instead of this fault, we create a fault in this line between 28 and 26, and then we create a fault. So, these three situations are to be distinguished by this swing center voltage approach and its rate of change of swing center voltage. Now, we see, you can say that the swing center voltage, how do you compute this? V cos phi, we have this V measurement at the M bus, at the local bus relay bus, and the corresponding phi angle between voltage and current. That V m cos phi gives us the swing center voltage. So, we plotted this one for the swing center. Derivative of this one gives us dSCV by dt. So, we have this one. So, now from this you can say that we see, can say that for this stable swing, we have a positive value of swing center voltage, and this is a going down some negative value, and then you can say that this perspective. Unstable swing, we know this unstable swing center voltage pretty oscillating, large value also, and it crosses the 0. Now, the derivative of that one is having consider also, you can say that like this pretty high value as compared to the stable swing case. Now, during fall, swing center voltage small value, derivative is almost constant. So, derivative is almost negligible. So, we see here swing center voltage is negligible and small amount is there, means fault. Swing center voltage, derivative of swing center voltage is significant, and it is swing center voltage oscillates, you can say that to 0, then this is unstable. Swing center voltage smaller value, and this derivative of swing center voltage smaller value, and swing center voltage is having a positive value, then we say this is stable swing. Thereby, we say that the swing center voltage approach can be applied, you can say that to distinguish fall from swing and stable and unstable swing for out of shape tripping business. The beauty of this method is that it does not require any system study in the setting perspective. So, in general we saw in this lecture three methods: incremental current only from the current signal, the R-Rdot approach to have, you can say, out of step tripping business, and then finally swing center voltage approach and its derivative we talk. The derivative gives information on that whether it is a to distinguish swing from fall and whether it is a stable swing and unstable swing in supplement with the swing center voltage decides. Now, however, we learned many techniques on to distinguish swing from fall situation for the power swing blocking, and for out of step tripping we have to identify whether it is unstable situation or not, and the out of step tripping is being accomplished at strategic locations only, which are predefined, and not you can say that at all locations for the distance relay. Note, there is a probability also that a fault may occur during power swing situation, because power swing is an elongated process. Disturbances are there in the large systems many times in a day or so. So, swinging situations will be observed by the relay frequently, but the power swing blocking will, you can say that, will be not be allowed, you can say that, to go for trip decision unnecessarily, thereby retaining the system stability. But the point is now, if a fall happens to be there in the system during power swing, if the relay has blocked, then becomes challenging. So, therefore, you can say that the blocking, you can say that, has to be removed during that situations to see the to clear the fall. Otherwise, you can say that there will be possible damage which is not desirable from the protection sense. Say if unbalanced fall happens to be there during power swing blocking, now what will happen that power swing is a 3-phase phenomena, balance phenomena, 3-phase. Unbalanced fall like line to ground or double line phase to phase fall or double phase to ground fall happens to be there. That means, the negative sequence component will be significant, which will not be found in case of swing also. So, by computing the negative sequence component as compared to the positive sequence component, we can distinguish this is a fault situation, and if it is a phase to ground fall, if the fault is involved with the ground, then zero sequence component also will be significant. So, they can be considered use, you can say that, to adjust the fault situation, and thereby consider the corresponding blocking functions can be removed from the relay. So, this is all on power swing blocking issues with distance relay. Thank you.